This talk is relatively on the applied side of that, where uh, in spite of talking about the crack growth, even if the crack is not growing, there are so many things which can be taken out for a structural engineer specifically. That is what is the topic for this talk. That is influence of cracks on nonlinear dynamics of beams. In fact, these are used. These outcomes are used by the for the structural health monitoring of the structures, which are basically vibration-based structural health monitoring. The contents which I'm going to cover in this talk is obviously introducing the topic what we are going to discuss, then types of the cracks which are considered for this modeling, and crack modeling and experimentations. So basically this will talk about the methodology, what we have adopted, then the effect of cracks on the dynamics, basically effect of the open cracks and effect of breathing and bilinear cracks on the dynamics. And finally, we'll take out some key observations. So by this, we'll be knowing that even if the crack growth is not happening, which is not desired in structural applications for the structural members, we don't want the crack to grow. At the very initial stage, it has to be identified and rectified, and the preventive action has to be taken care. So therefore, let us start with this talk. I'm talking about the effect of cracks on the dynamics of beams. Why? Because majority of the structural elements generally can be analyzed by the beam theories, the widely available beam theories. So if you talk about aircraft structures, if you talk about robotic arms, whatever structure, if you talk building structures, civil structures, bridges, those all can be modeled as a beam-like structure. So beam theories are quite workable in those applications. We'll be talking about the effect of these cracks on the nonlinear vibrations, because nonlinearity is an inherent in these structural applications. Most accounted nonlinearities which we generally account in structural mechanics are basically the material and geometric nonlinearity. Material nonlinearity, if we talk, it's nothing but this, as we all know, that is the behavior, the constitutive relations are nonlinear, and geometric nonlinearity will be basically talking about the large amplitude motions where the influence stretching cause the nonlinearity. So we'll see the effects of these cracks on these types of dynamic behaviors. I'll not go into much more detail of this vibration and nonlinearities here. Only we'll see the effects of cracks, how it is happening, and what are the takeouts for the structural engineers from these behaviors. Then we'll talk about the cracks. That is the most important part, that any structural element which is subjected to fatigue or cyclic or vibratory loadings, cracks are prone to happen, and these cracks are modeled in a different way. We'll see which type of models are being followed. And then finally, we'll discuss about the responses on these nonlinear structures, how these cracks respond this, and how a structural health monitoring engineer can take away and he can monitor by the vibration signals that the cracks can be identified. That is what we're going to discuss. Types of cracks which are modeled basically are open cracks, notches. As I already said, that I'm not going to discuss about the crack growth phenomena here. Generally, the open cracks are in type of notches which remain open throughout the cycle of the vibration. And these are classified: transverse cracks, slant cracks, and longitudinal cracks. There are several models are available. Breathing cracks generally, there's a confusion whether it is a growing crack or not, but breathing cracks generally, these are the cracks which are considered in this type of modelings are, they just open up to a particular length, particular crack length, and then they gradually open and they gradually close when the vibration happens. In half cycle they remain closed, in half cycle they remain open. In these type of cases, modeling is a bit difficult because the stiffness becomes a time dependent parameter, and then the behavior changes completely. Then there are surface and subsurface cracks, and crack growth, obviously, which I told that which is not a concern of this talk at least. If we talk about the modeling, if we talk about the open crack modeling, so open cracks are modeled as a typical notch, including local flexibility. So basically, whenever there's a crack in a structure, it induces local flexibility. In case of the open crack, this flexibility, this reduction in the this flexibility remains constant basically. So because of that, the overall stiffness which get reduced, that remains constant more or less in throughout the cycle of the vibration. That is what we mean by the open crack modeling. It is done in lot of cases, because experimentally the experimental setup is quite convenient to develop an open crack. You just develop a notch and do the testing, so it is easier. Breathing crack and crack growth modeling for dynamic analysis is complex as it involves time-dependent stiffness. As I told that whenever we talk about the dynamic modeling of breathing cracks, it involves time-dependent stiffness, because as the crack opens up and when it get closes, the stiffness becomes a time-dependent parameter, because the flexibility which is being induced is depending on time, depending on the cycle of the vibration. This breathing crack and crack growth, basically this breathing crack gives another phenomenon which is we generally term as dominant frequency. Although this dominant frequency is proposed as just a characteristic frequency, which is an averaged frequency of the overall response of the structure when there is a breathing crack. But subsequently, when the studies went, and we have already also verified that basically this dominant frequency, the resonant frequency was coming nearby this dominant frequency when we talk about the breathing cracks. Now, the modeling which we have done for the open crack modeling, so basically this is a beam and this is a crack. If you talk about the open crack, then this crack will remain open throughout the vibration cycle in the transverse direction. So this crack is modeled as a rotational as well as one extensional spring, and the left side of the beam is modeled as a different subbeam. Right hand side of the beam is modeled as a different subbeam. Both the subbeams are connected with the one torsional and one extensional spring. This torsional spring represents the discontinuity in the rotation at this crack location, and the extensile spring will take care of discontinuity in the transverse displacement in this particular crack location. In fact, if we talk about only the rotational spring, it will lead us towards the mode 1 fracture, which is the opening mode, and the discontinuity in this rotation displacement here at the crack surface, that will be proportional to the bending moment which is applied at this section. And similarly, the extensile spring will take care about the discontinuity in the transverse displacement at this crack location, and that discontinuity in the transverse displacement will be proportional to the shear force which is acting here, and that is basically the talking about the mode 2 fracture. Obviously, mode 3 fracture we are not considering here. Out of plane molding is not considered. Furthermore, we have also found that the system's total strain energy after considering the springs, the contribution of this extensional spring is insignificant compared to the torsional spring. That is because of the flexural vibration. Most of the structural elements are subjected to flexural vibrations, and we are talking about flexural vibrations. So the contribution of extensile spring can be further neglected because the effect of shear, in-plane shear, in particular in the open crack, is very negligible compared to the opening mode, the first mode. So if we model it by a rotational spring, then as I told that remaining in the framework of the linear elastic fracture mechanics and without touching the crack growth also, several beautiful outputs can be taken out for the structural engineers. That is what we are seeing. So a simple linear elastic fracture mechanics theory, if we follow, this G is nothing but the flexibility, and KT is the stiffness of this torsional spring. Once we obtain the stiffness of the torsional spring by obtaining the expression of this G, this is nothing but the flexibility. Don't confuse it by the Griffiths energy. This is just the compliance of the flexibility, and by that we will get the stiffness of the rotational spring. Once we get this, the total strain energy of the system can be obtained very easily. And I'm not going into much more detail of the vibration modeling of this particular structure. It is simply the energy method has been followed, or there are various methods which have been followed, and geometric nonlinearity has been considered because nonlinearities are inherent, and by doing that we'll end up by using suitable techniques, we'll be able to find out this eigenvalue equation. This eigenvalue equation is nonlinear because the stiffness matrix here is nonlinear. And for the open crack, as we know that there is no time dependency of the stiffness, it is quite easier to solve. Any general equation, we give the solution of this equation, Newton-Raphson Runge-Kutta, by any differential equation solver will get the eigenvalue problem, we can solve it. This equation we have particularly solved by just following an iterative technique. So we'll get the final response and we'll see how this cracks effects in the responses. Secondly, if we talk about the breathing crack modeling, there generally there are two models widely available. One is the bilinear crack model, where it is assumed that in one half cycle of the vibration, suppose this V is the vertical displacement of the beam. So in the upward cycle, a half cycle of the vibration, this crack will remain completely closed, so it will behave like an intact beam, and the natural frequency will be equal to the natural frequencies of the intact beam. And in the another half cycle of the vibration, this crack will remain completely open. That is what the bilinear crack modeling means, that it will remain completely open. So whatever flexibility expression we have obtained in the previous for the open crack modeling, that can be used for one half cycle of vibration, and for another half cycle of vibration, it will be zeros. So by this, the bilinear crack modeling can be done. If we specifically talk about the breathing crack modeling, there it is assumed that at one half cycle of vibration, the crack will remain closed, the beam will be intact, and in the second half of the vibrating cycle, the crack will get gradually open. Okay, and it will be depending on the displacement, and this displacement is basically coming from the nonlinear equation, so it is difficult to predict. So by that, the flexibility will be the open crack flexibility multiplied by the displacement, which is a function of time, by the Vmax, which is nothing but the maximum displacement. So now, if we convert it into stiffness, basically inverse of this, then the stiffness itself will become a function of the nonlinear displacement, which will be a function of time. So this modeling will be a bit different, and because of this, the frequency which we'll get at one half of cycle will get a different frequency. In the second half of cycle, where the crack is opening, there the stiffness is a time dependent parameter, so we'll get multiple frequencies, and by taking a harmonic mean of that all frequencies, we tell that the beam is vibrating with one dominant frequency, that is the dominant frequency that we'll get later on. Interestingly, we have also found, when we did the force vibration test, that the resonance is happening in the neighborhood of the resonant neighborhood of the dominant frequency. So that is what we're going to see. Talking about the experimental setup, what we generally do is we take the specimen, we prepare a notch, we put it into some cyclic loading, and if some fracture or some crack grows there, then we stop it, and then we put it in our smart shaker. Actually, it's a very old figure from our lab. Now we have a big electrodynamic shaker where we can test up to 1000 kg of load. So for the larger structure, we use electrodynamic shaker for the excitation. For the smaller for the lighter specimens, we use this smart shaker, which can take care of the excitation part. And excitation is given. The response is taken care by the sensors, which we generally use for the lighter sections. We use generally laser Doppler vibrometer, which is a non-contact type sensor. For heavier section, we can use accelerometers, which because the mass will not impact the dynamic behavior. For the lighter section, mass of the accelerometer, because it's a contact sensor, it will impact the dynamic behavior. So we use laser Doppler vibrometer. We connect it with the data acquisition system, and then by the post-processing software, we post-process the data. And we have found a very close relation between whatever modeling I have proposed with the experiments when we did it with the simple metallic beams. So I'll just talk about some of the results which we have obtained from last 4 or 5 years. This is a simple cantilever beam with a crack here, and we'll be talking about the open crack, how it behaves, the behavior of the dynamic. So the crack depth is taken as A. Although this analysis is done for a functionally rated material, here there is no scope, there is no point of talking about functionally rated material in the response, because we are generally talking how the crack is behaving to the dynamics of the structure. So only one response we will see. Basically, this one response is for the isotropic material. Beam parameters, everything is given here, and this is taken from our published article. This behavior is showing the first mode of vibrating frequency uh, with the crack location. We can see here, as the crack location is near in the neighborhood of the fixed end, the frequency is minimum. Although it's a common understanding that if the flexibility is being induced, then the natural frequency has to be reduced. But we can see that the frequency gradually increasing when the crack location is shifting towards the free end. In fact, this free end is the moment free end. So there is no bending moment. Therefore, there is no discontinuity in the cross section. So there is no effect of the crack. So for the first mode, the influence is like this, that the crack influences the dynamics when it is located in the neighborhood of the fixed end. When it moves towards the free end, the effect goes down. We also found it for different boundary conditions, and there are several factors which affect this severity of the cracks that I'll discuss in the conclusion slide, what exactly happens. If we talk about the second mode also, we can see here there is a bit variation here, because we have one vibrating node here in the second mode of vibration. So if somehow the crack is situated at any of the node of the vibrating mode, then there will be no influence of the crack, obviously, because there is no displacement at all, so there is no discontinuity. Otherwise, it will affect in the same manner, and same goes for the third natural frequency. Similarly, for crack depth ratios, if we increase the crack depth, then definitely the natural frequencies will reduce. For all the modes, the same behavior is obtained, and this is for the linear frequencies. Now, if we talk about some nonlinear attributes, when we model it nonlinearly, because nonlinearity is an inherent, so we cannot avoid. And we are talking now here the effect of the cracks on the nonlinear vibration behavior, and that too, now we are exciting that particular beam which was having one crack with some harmonic excitation f sin omega t. This is nothing but the displacement history of a healthy beam. The black curve is for the healthy beam, and the red curve is for the cracked beam. And this is a steady state response. Obviously, the amplitude we can see for the cracked beam, the amplitude is quite high compared to the uncracked beam. This figure we have obtained when we excited this system with the excitation frequency omega equals to half of the natural frequency of the system. Now, when we excite this system with another frequency, now the frequency of excitation has been changed. Now, at 0.33 of the natural frequency of the system, when we excite it, we got a super harmonic resonance here, and effect of cracks are prominent there. And we can see here that since we are exciting it with the 0.33 of the natural frequency, everywhere this effect is almost remaining same. For the crack also, only thing we are getting is the amplitude is being increased. Similar thing we observe in the phase plane plot of the same excitation frequency 0.33 from the natural frequency. This is a typical closed orbits we can find out in the phase plane portrait, and this inner orbit is showing about the crack depth 0. It means the intact beam response. Then gradually when we go out from this orbital, we are finding out when the crack is growing, the orbital response of the phase plane portrait is growing. That is because the velocity and the displacement both are growing in the same way when the crack is being the depth is being increased. If we talk about the harmonics of this response, how the crack is affecting the harmonics, when we excite this system with one single frequency like f sin omega t, where this omega is the excitation frequency is equals to 0.33 of the natural frequency, we found that the first harmonics is dominated by crack depth ratio 0.7. When the crack depth ratio is 0.7, then this first harmonic is dominating here. 0.7 will the crack depth 0.7 is having the maximum impact for this first order of harmonics. However, for the second, third, fourth order of harmonics, there is a slight response contribution of the third order harmonics here, but this response is almost same for all the crack depths. However, if the same structure, if we are changing the excitation pattern, and because the random vibrations, random excitations can come in any nature, Now we know that any periodic excitation can be written in terms of its higher order harmonics by using the Fourier series. So if we have changed this excitation pattern, and we have given it with a multi-frequency excitation, and we have changed the excitation to f sin omega t plus f sin 2 omega t with the same structure, and this omega being same as 0.33 of the natural frequency of the system, we found the response of the intact beam, that is in the black color, and the cracked beam which of the crack depth ratio 0.7, which is in the red color. This is the type displacement history, and this is a steady state response obviously, and these are the phase plane portrait. We can easily see that from the phase plane portrait we can easily identify the cracked response compared to the intact beam response. Interestingly, if we see same structure when we excited with different frequencies, the order of the harmonics which got changed. Now if we see the first order harmonics is basically dominated by intact beam, slightly more than the cracked beam response, and we can see here slightly at somewhere at this fourth order harmonics we have a very large dependent of this crack depth 0.07. So for the beam which is having a crack depth of 0.07, here with this excitation, basically the fourth order harmonics is dominating here, very high. Similarly, we can see that fifth order harmonics also is dominated by the cracked beam response. So takeout from here basically is the response of a cracked beam, although the crack is not growing, the response of the cracked beam which is in the form of either typical notch. So we have discussed about the open cracks here, so which is in the form of a typical notch. There are various applications which can be possible, and there are various takeouts which we can take from here, that even if the system is same, if the excitation is different, the crack is going to behave differently. The modal parameters of the structure is going to perform differently, and the steady state response which is coming from the excitation, which will be significantly different. So this is one takeout which from structural engineers can take for the structural health monitoring purpose. The second thing is the response of a breathing crack modeling in the dynamics of the beams. Now same structures we have taken, and as I told that in the breathing crack, basically we talk about the dominant frequency, and how we get the dominant frequency is, since in the breathing crack, as I have already showed you, that the flexibility will be time dependent. For 1/2 cycle of the vibration, the stiffness will remain constant, or it will behave like a intact beam. For another half cycle of the vibration, the flexibility will be induced, but the crack will grow gradually, and therefore the flexibility will be a time dependent term, and hence the stiffness. So since stiffness is a time dependent term, if we take different instant of times, the frequency will come different. So therefore this frequency, or the breathing frequency, is taken as the harmonic mean of all the frequencies taken at different instant of time in 1/2 cycle of vibration, and obviously for 1/2, that is pi, it will be nothing but the frequency will be the frequency of an intact beam. So when we took this, we got the dominant frequency, and interestingly we performed the force vibration with that structure, and we found that the resonance was coming in the neighborhood of this dominant frequency. Although it was just an average of that, the harmonic mean of that, but the resonance was coming in the neighborhood of this instead of in the neighborhood of any closed beam frequency or the completely open cracked beam frequency. This is the response which is showing with the crack depth how the frequency is changing for open crack model, for bilinear crack model, and for the breathing crack model. For the open crack model, the reduction in the frequency is quite high. It's very large. For bilinear crack model, the frequency is in between the breathing crack modeling, and for the breathing crack modeling, it is more accurate, and it's a more accurate modeling obviously because the crack is opening and closing in the time, and this reduction is plotted here. This is the response for this is a time response, and this is not a steady state response. That's why it is looking a bit hazy. So this is what I had to talk about what we can take from, even if the crack is not growing, because we assume that the engineering structure will not fail by cracking. But somehow, if some crack gets developed, and we perform the online condition monitoring, online vibration testing. So if we have the vibration data from the operating structure, by seeing the shift in the response, we can clearly identify where the crack is. Uh, there are various techniques also by using this response, the identification of the crack. Basically, there are two different techniques. One is the forward method, which I showed when we know the crack parameter and modeling it and getting the dynamic behavior. Another is we take the vibration response, which is more practical. We take the vibration response, and out of that we try to measure what are the crack parameters if there is any crack. So that is inverse method, and what we generally do. So this is what I wanted to tell about how the crack affect the dynamic of the beams, and there are so many things to take out for the structural engineers. More or less, what we have discussed and the key observations are reduction in the natural frequency. That is a very key fact, that whenever there is a crack or whenever there is a flaw, because of the local flexibility, the induction of the local flexibility, the natural frequency will reduce. That is a sure shot phenomena that is going to happen. Severity of the crack on the dynamic behavior varies with boundary conditions. Now, with boundary conditions means, if we talk about the clamp structure, if there are some point of contraflexures, and in the point of contraflexures, if the cracks are there, then there will be no effect of the cracks. If we talk about the second mode of vibration or third mode of vibration or higher mode of vibration, and if there is a vibrating node where the crack is locating, so we'll not get any response from the crack. We will not get any effect of the crack on the response. So location of the crack, same. So location of the crack also matters. The effect of cracks on nonlinear dynamics is highly dependent on the excitation. We have also seen that the same structure, when it is excited with a single frequency excitation, we got a different type of response. Basically, the dominance of a particular mode was happening in some particular cases for intact beam, and same was completely changed when we saw with the two frequency excitation or multi-frequency excitation. When we excited with a different excitation pattern, then the crack affects the different modes differently. That is what we have seen also. And dominant frequency, this is one concept which also is a takeaway, that if there is a crack, generally crack are present in nature, the fatigue cracks. So the resonance, which the structural engineer, we generally try to avoid. So that will be closer to the dominant frequency, not to the frequency which we get from the open crack modeling, or not to the frequency which we get from any bilinear modeling. So it is basically closer to the dominant frequency, and dominant frequency is relatively different from what we get from the open crack modeling. So that is all for this talk. Thank you. I'm open to you all.